Hello folks, welcome to CodeCrucks. In this video, we will discuss DFA minimization using equivalence matrix. In previous few videos, we have already discussed minimization of DFA using state minimization method. This is the another way of minimizing the DFA where we are constructing equivalence matrix and from that we will generate minimized DFA. As a prerequisite, you need to know equivalent states concept, which I have already discussed in one of my video. The link of that video is given in description box. For this method, we have to start with construction of initial equivalence matrix, that is E of 0. In any equivalence matrix ek of I comma j, we have to evaluate the equivalent states. So if state qi and qj are equivalent for any string having length less than or equal to k, we have to set ek of I comma j is equal to 1, otherwise it is 0. So E is the equivalence matrix, k is the iteration. So we have to compute E of 0, E of 1, E of 2, etc. Whenever E of k and E of k minus 1 are same, we have to stop. So in any equivalence matrix E of k, we have to set ith row and jth column as a 1 if and only if qi and qj are equivalent with respect to all the strings of length less than or equal to k. We only need to calculate the upper triangle of the equivalence matrix because equivalence matrix is symmetric around the diagonal. So whatever elements we have in upper triangle, the same are there in the lower triangle. So we will omit the computation of lower triangle to reduce the complexity. Let us see how to construct this equivalence matrix. So first we have to start with initial equivalence matrix, that is E of 0. Now E of 0 we can compute without much processing. E of 0 I comma j is 1 if qi and qj are both in final state or both are non-final states. So this is also called P0 partitioning or zero equivalent, as we have discussed in our state minimization examples. And E0 of I comma j would be 0 if qi is final state but qj is non-final state, or vice versa, that is qi is non-final state but qj is the final state. So construction of equivalence matrix is pretty straightforward. We just need to evaluate the pair of states qi and qj. And if both are in the same category, then we will set E0 of I comma j as 1, else we will set it to 0. And this is the algorithm to build initial equivalence matrix, that for I is equal to 0 to n minus 1 and for j I plus 1 to n, we have to check if qi and qj both are in set of final states, that is capital F, or both are non-final states. In that case, we will set that particular ith and jth cell in E of 0 as a 1, otherwise we have to set it to 0. Consider this is the DFA that we wish to minimize or for which we want to construct equivalence matrix, initial equivalence matrix E of 0. To construct the equivalence matrix, we have to check out all the possible pairs, that is state 0, 1, 0, 2, 0, 3 up to 0, 6, then 1, 2, 1, 3, 1, 4 up to 1, 6. Similarly 2, 3, 2, 4 and so on, because we only have to construct the upper triangle. So state 0 and 1 first we have to evaluate. So state 0 is non-final state, 1 is final state. So they both are in different sets. So we will set E0 of I comma j, that is E0 of 0, 1 as a 0. Next, if we evaluate 0, 2, then 0 and 2 both are non-final states. So we will set E0 of 0, 2 cell as a 1. Same is true for 0, 3. For 0, 4, state 0 is non-final state, set 4 is final state. They are in different groups, so we have to set 0, 4 in equivalence matrix as a 0. And then 0, 5 both are non-final, 0 and 6 both are non-final, so we are setting it as a 1. In same way, now we have to evaluate for the 1, 2, 1, 3, 1, 4, 1, 5 and 1, 6 pair. So only 1 and 4 both are final state, so that particular entry will be 1. Rest in all remaining cases 1 is final, but 2, 3, 5 and 6 are non-final. So we have to set them as a 0. And in similar way, we can compute the pair 2, 3, both are in same category. So we will set 1, then 2, 4, they are different. So we will put 0, then 2, 5 and 2, 6 are identical group. So we will set it as a 1. And same way we have to construct. So this is initial equivalence matrix. From this, now we have to construct E of 1, E of 2, E of 3, etc. until two consecutive equivalence matrices are same. We will repeat this process. So to construct the consecutive or the subsequent equivalence matrix, what we need to do is we have to find out the transitions on all input alphabets A from state Qi and Qj from the initial equivalence matrix, and assume that those transitions are Qx and Qy respectively. So now we have to check if x, y position in E of m minus 1 is 1, then we have to set I, jth position in the E of m as a 1. That is, again I repeat, we have to find the delta transitions for all the input alphabets A, B, C, D, etc. for all possible pairs in equivalence matrix, and assume that those transitions are Qx and Qy respectively. Now we will check the x, y cell in the previous equivalence matrix. That is, we are constructing right now E of 1. So we have to look into E of 0. If on x, y position in E of 0, the value is 1, then ith, j cell in E of 1 we have to set as 1. And otherwise, we will set that location as a 0. So this is the algorithm for that. We will start with m is equal to 1 because E of 0 is already constructed. For I is 0 to n minus 1, for j is equal to I plus 1 to n, for every alphabet A which belongs to set of alphabet sigma, we have to repeat this process. So first we will compute x as a delta transition of Qi, A and y as a delta transition of Qj on A. And now we will check if E of m minus 1, that is the previous equivalence matrix, is having value 1 on xth row and yth column, then in ith row and jth column of E of m, we have to set it as a 1, otherwise we will set it to 0. Increment m by 1, so now we will compute E of 2, then E of 3 and so on. And this we have to repeat until no changes are made to E of m and E of m minus 1. Let us understand how to do that. This is what we have already constructed. E of 0 we have derived from this for this diagram. Now we will only evaluate the pair where we have entry 1, because only those entry can be changed. Wherever it's 0, we don't have to touch. So we will not do anything for 0, 1 cell. We will start with 0, 2 because there is entry 1. So this entry may be 1 or may become 0 in subsequent matrix. So for 0, 2, first we will find out what is the transition on input A from state 0 and state 2. So x is equal to delta 0, A. So if we read A from state 0, then we can see from this DFA, it leads us to state 1. And if we read A from state 2, then it leads us to state 0. Now we have to evaluate E0 of x, y. So x is 1, y is 0. So we have to evaluate E0 of 1, 0. That is the first row and 0th column, or 0th row and first column. Both are same because matrix is symmetrical, right? So E0 of 1, 0 here is 0. That means we have to change E of 1, 0, 2 to 0. Here I is 0, j is 2. So that particular entry in the next equivalence matrix, that is in E of 1, we have to set to 0. Let us consider next pair, that is 0, 3 because it is having entry 1. So we have to check whether that entry will remain 1 or it will be converted to 0. So for 0, 3, again we will find out x, that is delta 0, A which leads to 1, and delta 3, A which leads us to 4. And here E of 0 x, y is equal to E of 0 1, 4 because x and y are 1 and 4 respectively, and that is 1. If it is 1, then we have to keep that particular ith comma jth cell in E of 1 as a 1. So E of 1 0 comma 3 will remain 1. Next pair is 0 comma 5. So if we evaluate that, x is 1, y is 3, and that 1 comma 3 position in E of 0 is 0, and that's why the 0 comma 5th cell in E of 1 we have to set it as a 0. Next pair is 0 comma 6. Again we will find out x for that, y for that, and it gives us 1 comma 5 and 1 comma 5 or 5 comma 1, vice versa, both are true because matrix is symmetric. So that entry is 0, and that's why we will set E of 1 0 comma 6 to 0. In this way we will keep computing. So this is the computation for first row. In second row we have to make a computation for cell number 1 comma 4 because there is entry 1. Now depending upon the conditions, this may remain 1 or it may be converted to 0. But this is how we will keep filling this and we will produce E of 1. Now E of 1 we have to use as the input matrix, and from that we have to generate E of 2. Once computation of E of 2 is done, we will use E of 2 as our input and we will construct E of 3 out of that. And this process we will continue until some E of k and E of k minus 1 are identical. Once they are same, we will stop, and from E of k we will generate the minimized DFA. So this is the algorithm or the basic procedure. In next video, we will take one example and we will show step-by-step construction of equivalence matrices and the construction of minimized DFA. Thank you. That's it for today, folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.